Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. Alright, welcome to 8.3 Inverse Kinematics on the set of displacements, part of the Displacement Matrices and Inverse Kinematics chapter. Alright, let's jump in. Recall the inverse kinematics problem, introduction, in section 3. We are given a desired configuration for the end effector of the robot, and our goal is to compute joint angles that achieve the desired configuration. In chapter 3, we studied and solved the inverse kinematics problem for a two-link planar manipulator arm, with links connected by revolute joints. See figure 316. Let's actually see figure 316. Let's go ahead and click on it. Here it is. This is the one that we looked at before. Okay. For the two-link robot, we could compute the joint angles θ1 and θ2 using geometric arguments. However, for more complex robots that have higher dimensional configuration spaces, such calculations are very challenging. In this section, we will see how reference frames and displacement matrices can be used to solve the inverse kinematics problem. All right, it's a more systematic approach, which of course we prefer for complicated problems, right? Multi-link robots. Multi-link robots are made for a variety of purposes, from the larger industrial automation robots as shown in figure 8.3. So we have these big robot arms that are used in an industrial setting, typically some sort of manufacturing setting, and smaller assistive robots as shown in figure 8.4. So here is a smaller robot which would be assistive for maybe somebody who needs help moving an object around in a home environment, say. So, for many applications, a common design is to have a base consisting of 3 links connected by 3 revolute joints. The base is used to position the end effector. The end effector, or gripper, is commonly attached to the base using a spherical wrist. Okay, we looked at those in an earlier chapter. I forget which chapter. The wrist is used to orient the gripper at the desired position. Okay. Multiple frames and loops. Consider an environment with multiple frames and corresponding displacements that form a loop as depicted in figure 8.5. So here we go. We have multiple reference frames, and these reference frames are related to each other in a loop, in that this one is related to that one, is related to that one, is related to this one, is related to this one, is related to this one. Okay, so you can go around this way if you wanted to, or you could go around this way if you wanted to. Those are the loops. In general, we know that Hij is equal to the frame sigma I expressed with respect to sigma j. We consider the following sample problem. Assume we know all matrices corresponding to the displacements illustrated in figure 8.5. So we know how to go from sigma 0 to sigma 1 with H1 0. Okay, H sub 1 super 0. And H sub 2 super 1 gets us from sigma 1 to sigma 2. Similarly, you could go this way and you could say H30 is this transformation. H4 in terms of 3, so H43 is sigma 4 in terms of sigma 3, and sigma 2 in terms of sigma 4 would be H24, sub 2 super 4. Now, we know all the dark arrows here, but we don't know this relationship. Okay, we know all of the other relationships in the loop except this one. So we're going to express this one in terms of the others. Okay, so that is H10, H21, H30, and H24 are all known. except for the displacement matrix H4, 3. So we don't know H4, 3. We don't know sigma 4 in terms of sigma 3. How would you compute H4, 3? So let's write down the known facts and obtain the loop relationship. So we know that H20 is H10, H21, subscript matching with superscript. Looking up here, so if we traverse the upper part of the loop, we can say that H20, sigma 2 in terms of sigma 0, is H10, H21. Similarly, we could go the other way around. So we could go down this way, which would be H30, which we know, H43, which we don't know, and then H24, which we know. So that's what we've got here. So 4, 3 is the one that we don't know, and we would like to solve for it. Let's just equate these two equations first. So let's say that H20 and H20, these must be equal to each other. These right-hand sides must be. And so let's write the first right-hand side right here, and then let's write the second right-hand side down here. So they're equal to each other. Therefore, we can simply solve. These are just matrices, right? So H43 is left multiplying the inverse of H30 over here, and right multiplying the inverse of H24 gives us H43. So there's our solution. Pretty nice. The pick-up in place problem. Consider the pick-up in place problem illustrated in figure 8.6. So this is the figure. We've got a robot with a base and a joint 1, revolute joint 1. We have revolute joint 2 and revolute joint 3. The gripper is at the end. We have a table and an object on the table. Our goal is to use the robot to grasp the object sitting on the table. Okay, so the gripper to the object. This task is an instance of the inverse kinematics problem. Okay, so it's an inverse kinematics problem. We want to go from the workspace to the configuration space or the joint space, right? So let's look at this step by step. 1, the reference frames sigma base, sigma gripper, sigma table, and sigma object shown here. So base, gripper, table, and object, those reference frames, describe the placement and orientation of relevant objects in the environment. Each link of the robot, i.e. each rigid body component of the robot, is described by a reference frame, sigma 1, sigma 2, sigma 3. So we see sigma 1, this first link, sigma 2, second link, sigma 3, third link. So those are our reference frames. Okay, as an aside, so this is not in the direct solution that we're looking at now, but let's talk about it for just a moment. A systematic methodology to place frames in each link of a robot is the Denevitt and Hartenberg, or DH convention. This is popular. So this Wikipedia page has more clarifying that convention. It's a nice convention to use, so I do recommend using it, but it's a bit of an aside for now. Once frames are placed, we should have an expression for the displacement matrices. So H1 with respect to the base in terms of theta 1. So H1 is going to be what is sigma 1 in terms of the base reference frame, and it should be a function of theta 1. It's just a rotation, right? And then a displacement of the origin. Okay. H2 1 is H2 1 is sigma 2 relative to sigma 1, and similarly H3 2 is sigma 3 relative to sigma 2. So these are each a function of the joint angle associated with that body. Because of the way the gripper works, the gripper and object need to be at a specific desirable relative displacement with respect to each other. Okay? They aren't necessarily going to be at the same point. They might be some displacement from each other. So that is the, we'll call this the H desired. So denote this object displacement with respect to the gripper as H desired. So that's the desired displacement between the object we're picking up and the gripper. Then the correct grasp takes place when H object to gripper is H desired. So the position of the object relative to the gripper is equal to H desired. 5. Now we can apply the same ideas as in the previous discussion about multiple frames and loops. First, let us study the object with respect to the gripper. Okay, this displacement is H desired equals H object in terms of the gripper, which is equal to H base in terms of the gripper times H table in terms of the base times H object in terms of the table. Notice again, subscript matching with superscript. We want to go from the gripper base relationship to the gripper object relationship, right? That's what we've done. The base and base effectively cancel here, and the table and table effectively cancel here, and we get the gripper object relationship, which is what was on the left-hand side of the equality. So we've now written it in terms of gripper and object. And the reason we've done this last inverse here, because this previous expression was also true, is that the gripper base relationship we know usually in this order. The relationship of the gripper in terms of the base and not the reverse. So what we know now is the object gripper relationship, okay? The object gripper relationship is gripper object. So we went around from gripper and base and table and object. We did that sort of part of the loop, if you will. And now we're going to go the other way, and we're going to talk about how to go through the robot itself to get to the gripper. So we related the gripper to the object, and now we want to relate the gripper to the robot, if you will, through the robot. So, good. So 6. Second, let us study the gripper with respect to base displacement, which depends upon the robot joint angles, i.e., the robot forward kinematics. So the gripper in terms of the base relationship or displacement is H1 in terms of the base, the first link displacement in terms of the base, the second link displacement in terms of the first link, the third link displacement in terms of the second, and then the gripper in terms of the third. So we've gone along that chain from the base to the gripper. Previously we went from the base to through the table object to the gripper. Now we went this way. But we know that those two things must be equal since they both express the position of the gripper in terms of the base. So finally, to place the gripper at the correct displacement, plug equation 8.4 into equation 8.3. So 8.4 is H gripper base, 8.3 is H object gripper, and we can simply plug in H gripper base into here, and we have an expression from which we can solve for the joint angles, which we would call the robot inverse kinematics if we solve for those angles, right? Solving equation 8.5 is akin to computing Euler angles for a rotation matrix. Trigonometric calculations are typical. To continue the analysis, we draw the manipulator in figure 8.7 in a somewhat more detailed form. Measure some distances and write down the 3 relevant displacement matrices as functions of the joint angles. So now we're going to get more specific about what those relationships are. Each of these links has a length associated with it, and each of the joints has an angle associated with it. So we can write the H1 base relationship, which is to say member 1 in terms of the base coordinate system or reference frame. And we have a rotation about z, theta 1, and a fixed displacement L1. Okay, that's what the L1 denotes. H2 to 1 is a rotation about the axis x, and theta 2 is the angle of that rotation. We have a displacement of L2, a fixed L2 displacement there. So we see that one given by the relationship between sigma 1 and sigma 2. Okay, h3,2 in terms of theta 3 is the rotation about x of theta 3. So we see that this x rotation is again what we get for sigma 3. And we write that in terms of sigma 2. There's a displacement of L3, the displacement from this joint to this joint. Okay, finally we have the gripper. So h gripper 3 is no rotation, so we're assuming that this gripper has no rotation relative to member 3, but we do assume that it has a displacement. It's offset by L4 in the y direction, okay? So it's offset by L4 in the y direction, denoted here. After some careful bookkeeping or some symbolic computations on a computer, highly recommend that, we obtain this. So h1 base, h21, h32, h gripper 3, which if you go back up here to our expressions, is this left-hand side, can be computed out from these expressions for those objects that we came up with. We get r gripper base, so the rotation matrix between the gripper and the base, and O gripper base, the displacement of the origin from the gripper to the base. Okay, and you can actually work out what these are in terms of these basic rotation matrices from before, and here they are, worked out for you. In what follows, we are only interested in setting the location of the end effector equal to that of the object. In other words, we consider only the 3 translation components of equation 8.5, and we only aim to find the angles theta 1, theta 2, theta 3 such that this holds, where v1, v2, and v3 is the translation vector of the displacement matrix given here, so the right-hand side of 8.5. This is an inverse kinematics problem, as stated before, and we can solve for those angles. Suppose we look for solutions where theta 2 is between negative pi over 2 and pi over 2, and theta 2 plus theta 3 is in the range negative pi over 2 to positive pi over 2, so that the corresponding cosines are strictly positive. Then we have the following equalities. Theta 1 is this arctangent of v1 over v2, the negative sign in there. Similarly, we have these relationships between theta 2, theta 3, and the L's and V's. The last two equations are identical to the ones we solved for the two-link manipulator, see proposition 3.1, which includes a solution for that. So theta 1, theta 2, and theta 3 are solved for this example. Of course, you need specific lengths and you need specific displacements of the object relative to the base and all that. But once you have those, you can compute what angles you need. So I encourage you to actually plug in some numbers here and give it a try. Okay, so notes and further reading for this chapter. For treatment of multi-link robots, we refer to a comprehensive robotic text such as Spong, Hutchinson, and Vidyasagar, Murray, Lee, and Sastry. Okay, so those are two pretty comprehensive robotics textbooks. All right, I'll see you next chapter. Take care.